Okay, today I want to talk about Kirchhoff's voltage law and Kirchhoff's current law. The first thing we're going to do is um, they're basically Kirchhoff's voltage law and Kirchhoff's current law or application of Ohm's law. Okay, and this basically specifies the relationship between resistance, current, and voltage in a circuit. So the voltage drop, you could say, is equal to whatever current, voltage drop across a resistor is equal to whatever current is traveling through that resistor times that resistance of that resistor. Now, of course, this applies to multiple resistors too, so this could be a combination or equivalent resistance. It's whatever the current's going through that combination times whatever the resistance is equal to that voltage. Okay, so we're going to apply Kirchhoff's current law and Kirchhoff's voltage law today to solve some unknown values in some circuits. Okay. The second part of this is that there's the power law, which I'm not going to cover today necessarily, but once you know the voltage drop across a resistance value and you know the current through it, it's very easy to figure out the power. Okay, so that would be like the final step. You could actually go through and do that very easily. And in general, what you're going to find is that power is just uh, or energy is converted basically over to heat in a resistor. So this is the relationship. You know the voltage, you know the current from either current through resistor, voltage drop across resistor. You can figure out the power that it's dissipating. This is also for a source too, a voltage source or a current source, power source. It's the voltage times the current. Okay. So first part here, we're going to talk about Kirchhoff's current law. And the idea here is essentially if you think about, maybe water traveling through a pipe or something, and maybe this is like a split, some kind of crazy split here. And you have water flowing in, and maybe this is coming in, this is water flowing in, this is water flowing in, this is coming in to this junction, and then it's leaving this junction. And this could be some kind of multiple uh, Y connection or fork connection. Um, and you'll see that whatever rate this one coming in plus the rate that this one's coming in plus the rate that this one's coming in must equal the rate of these two together, right, at which it's coming in, right? Nothing's going to happen to that water or current flow. So you think about this as like a water junction. It's essentially the same thing as if it was a current junction. Current is just flow of electrons or its quantity of charge per unit time, while water is, volume per unit time, or quantity of molecules, water molecules per unit time. Okay. One of the things you need to pay attention to is that in this case, what we would say is that, and you can do this either way. This one actually has current is positive coming in, and it's negative leaving. So you'll see the negative signs here. I2 and I3 are the ones that are leaving. I4, I1, I4, and I5 are all coming in, so those are positive. Okay, and this is the general form of that expression, just saying that, general form of the equation that represents Kirchhoff's current law just says that summation of all the currents coming into a node or connection point of our devices is going to be equal to zero. Okay, all right. The second part of this is Kirchhoff's voltage law. Okay. Now, you could use a water analogy for this one too. We could think about like this is a voltage source, a battery, some power source, power supply, let's say, for your computer or some other device. And what it says essentially is that we're giving energy to the electrons through a power source, and the energy is being lost. The energy is being lost as the electrons travel through these devices, where they get back to whatever this reference point is energy. This gives it energy, and that loses energy. And when they lose energy, electrons are traveling through or electrons are charge carriers. If we want to think about it that way. Um, when they lose energy, they're actually going to dissipate it as heat, and that's where we get the power. If you were to connect resistors up to a power source, you're going to find that these are going to heat up somewhat. Okay. But the basic idea is this. Whatever energy you give to the charge carriers, let's say, whatever you increase it, it's going to be lost to get back down to this reference point. It's almost like if you think about this as maybe like you take water, you lift it up on a water tank, and then the water falls back down through some pipes or something, back down to the ground again, and then you lift it again, and it falls, and you lift it again, and it falls. So what we're saying is whatever amount of energy you're giving to those charge carriers, you're going to lose it and get back to essentially whatever the reference point here is, which could be zero, let's say. Okay? So what you're saying is that you sum all of these in any loop in your circuit. So we can look at circuits and we'll look at the different loops when we actually look at some of the problems. If you sum those, it's going to be equal to zero. Okay. Now in this case, you have different ways to represent this. You could have it go. You could actually do the loop in the other direction. It really doesn't matter. One of the ways you could say is that whatever voltage this increases, you lose it over here. So you could actually say like V minus V1 minus V2 minus V3 equals 0. Okay. You'll see different representations of this equation. Sometimes they reverse it and do negative V plus plus plus, and it will come out to be exactly the same. Okay. This is a common form that we're going to look at. We're just basically say, okay, you give energy, that's a positive voltage, negative, negative, negative. Okay. Okay. So I'm going to take a look at, so this is basic idea, right? We talked about the relationships and then voltage and current laws. Both of those are algebraic sums equal to 0. Okay. So what I'm going to do is look at a couple of examples to show you this in action. So let's start with this. Here's one of the problems from the homework. So I'll discuss this. I'll go through it with the author's solution. Okay. So you have here you have a 50 volt source, independent source. So this could be a battery, 50 volt battery, right? And these are just some resistors and they're connected in this configuration. Well, we see that we have a closed loop here, and you can actually draw like a loop. You could say, oh, here's a loop. Electron's going to flow this way, back to the source, and then here's another one. Going to go around, go through here, go back around, and go back to the source. So there's actually, you could see there's actually kind of two loops here. There's one inner loop, and there's an outer loop here. Okay. So when the electrons travel through these, of course, they're going to lose energy, and when that happens, you get a potential difference or a voltage drop. Okay. So we're going to use both concepts. We're going to use the concept where summing all, and if you look at this, you'll see here's a node here, right? So electrons travel through here, and they split. Part of them goes this way, part of it goes, electron flow goes this way, and part of our current flow goes this way. And then they come back together, and it flows through here, and then back to our source. And what you would recognize here is that this resistor, whatever current is flowing through here, is the same current that's flowing through our source, okay? So that kind of simplifies it in a way, is that, oh, so whatever's leaving here, we could call that one I1 or something, or I through the 22 ohm resistor, is whatever's going up here, and then it splits, and then it comes back together, okay? So we use these concepts. So if we look at the circuit first, like I said, we identified two loops here. We can also identify the nodes or the connection points. If we look here, this one is connected to here, it's connected to here. So this is like one node or one connection point. We have another one here where this one and this one are connected and they're connected to here. We have another node here, okay? And the third node or connection point or junction is connecting this 22 ohm resistor to the negative side of the 50 volt source, okay? So this circuit has two loops and 1, 2, 3 nodes, okay? So we're going to use both those concepts. We're going to use KVL and KCL to solve this circuit, all right? Okay, first thing. We start off, like I said, we can identify the two loops. We can identify a node here, node here, node here, whatever. But what we're really going to get to a point is that, it depends upon how many unknowns we have, right, in our equations. If I find that I need to solve the circuit, I need to I have two unknowns, then I know I can solve the circuit with just two equations, okay? And what we're going to end up doing in this particular problem is we're picking a node here, and I1. Essentially, it's the same thing here, right? This is I1, I2, and I3. So this really doesn't really do anything for you if you did another node equation down here. Essentially, it's the same equation we have here. Okay, so you can write it like this. So we could say that here's a node. I have current coming in and then current leaving. And the second equation I could come up with is that I can draw a loop here. And I could do the outer loop. I could do the inner loop. It really doesn't matter. But I have a second equation here where I'm going to sum the voltages and set those equal to 0. Okay. The first part is just saying some assumptions. Voltage source is ideal. All that really means is that, when you have a real voltage source, usually they have like some resistor that's part of it. So it makes it a little more complicated in terms of the analysis. But for us, ideal voltage source, all we're saying really is that there's no internal resistance, okay? There's nothing else that we can just represent it this way. And that's all, in this course, that's all we're going to do is deal with ideal sources, so it really doesn't matter. The connecting wires is negligible, so there's no resistance, right, of these wires. In reality, and there are always a little bit of resistance, but usually it's so small we can just ignore it, okay? And then the resistances of the resistors are constant. Okay, well, these three things are always the case for us in this course, okay? So we have just basic circuits to start with. If you're going to if you're going to do like electrical engineering or do some electrical circuits courses, then of course these models of these real devices, which is all we're really doing here, we have math models of these real devices, get to be more complicated, okay? But for this course, this is for all of them. So you can just draw it like this, which is perfectly fine. Okay, so here's our governing equations. Of course, Ohm's law. Here's my here's Kirchhoff's current law and Kirchhoff's voltage law. Okay, so the first thing we want to do is, well, here's the assigning of the resistors. That's already defined. So we're going to apply KCL at the node. Okay, and we've already drawn it and said that, oh, okay, we're going to use this node to come up with a KCL equation. Okay, so I1 was coming into the node, and I2 and I3 are leaving. So I1's positive, I2 is negative, and I3 is negative. And that's what we have in our circuit. Coming in and leaving. Okay. The next thing we're going to do is we want to write those KCL equations in terms of voltages over resistances. Okay. Remember, it's V equals I times R. So I equals V over R. So for the first one, what we're going to say is for R1, and actually, it's even though the author wrote the note up here, since this is the same, this is I1 right here, we can actually write it as this being our resistance R1, this being my 22 ohm resistor. Okay. So if we look at it, it's just going to be V1 over R1, which is the 22 ohm resistor, V2 over R2, and V3 over R3. Okay, so V2 and V3. One of the things you're going to recognize here is that this resistor, the 75 ohm and the 333 ohm, both share the same two nodes. Node up here and the node down here. Okay. So since that's the case, what we're going to find here is that the voltages will be the same across both of these. Okay. And this is just like, if you have two parallel resistors, what do we find? That, if they share the same nodes, they're in parallel, which means essentially that the voltage drops across the two are the same. Okay, so we make that simplification here. So now we just substitute in and say, oh, okay, V2 and V3 are equal to the same, so I just substitute in V2 for here. And we just break it out, pull out the V2, and then we have an equation now for this circuit where we have just two unknowns. Okay, so now what we need to do is come up with another equation so that we can make a substitution, our second equation, and then substitute in for one of these unknowns. Okay, well, let's look at using KVL, right? And the loop we're going to follow here is just this. We could follow this inner one. It really actually doesn't matter because they both have the same voltages. You're going to come up with exactly the same equation for that. But the basic idea is this. You go up by some voltage. So you're at this point, and that's 50 volts, right? It's already defined because that's our voltage source. And then you go down by some voltage. And then you go down by another voltage. And those, now you're back to your reference point or your starting point, right? So just increase the charge carriers, give them additional energy, lose energy, back to where you were when you originally started. So we're going to go up by 50, go down by, this one would be our V2, and we've defined this one as V1, so then go down by V1. So the equation just becomes 50 minus V2, I'm sorry, minus V1 minus V2. Okay? Then what we could do here is, if you notice, that we could take our V1 and just pull it over to the other side, and V1 now would be equal to 50 minus V2. Okay? So we substitute in 50 minus V2 for my V1. Okay? Now I have an equation where I have an equation where now I can go ahead and solve for V2. So all you need to do is, you can rearrange this, and then you can solve for